Let's find the potential field of a point charge at the origin. I've placed a point charge Q at the origin, and we know the form of the electric field intensity due to a point charge at the origin. Let's pick two arbitrary points, A and B, and find the potential difference between B and A, V sub B minus V sub A. We know that potential difference is equal to minus the integral from A to B of E dot dl. The position vector of point A is R sub A, and the position vector of point B is R sub B. Let's substitute for our electric field intensity. We have a unit vector in the R direction dotted with a differential length. That will just be our differential in the R direction dr. You can verify this by taking the dot product of the unit vector in the R direction with the differential length in spherical coordinates. AR dot AR is 1, giving you a dr, AR dot A theta is 0, and AR dot A phi is 0. So with this substitution and pulling out the constants to the left of the integral, we have minus Q over 4 pi epsilon sub 0, the integral of dr over r squared. At location A, r has the value r sub A, and at location B, r has the value r sub B. So our limits of integration become r sub A and r sub B. The integral of dr over r squared is minus 1 over r, so this becomes Q over 4 pi epsilon sub 0 r evaluated at r sub B and r sub A. So for a point charge at the origin, the potential difference between 2 points is Q over 4 pi epsilon sub 0 times 1 over r sub B minus 1 over r sub A. The potential difference is independent of theta and phi. It just depends on the distance the 2 points are from the origin. To understand this dependence only on r, let's think about moving from point A to point B along two different paths. Let's first move from a distance RA to a distance RB at the same value of theta and phi. Now move to point B by varying theta and phi. Along this path, all the work was done when we were moving along the radial direction. When we were then moving perpendicular to the electric field, no work was done. Now let's first move in the theta and phi direction as shown here. And then just move in the radial direction to get to point B. We start out moving perpendicular to the electric field, so we do no work along this path here. All the work is done then when we're moving in the radial direction to point B. So for both these paths, the only time work is being done is when we're moving in the radial direction. And that's why the potential difference between two paths only depend on the distance the 2 points are from our point charge at the origin. If I move in the theta and phi direction and keep a constant distance from the point charge, the potential does not change. Let me rewrite our description of the potential difference, indicating the dependence on just the radial component r. So I can replace V sub B minus V sub A with V at R sub B minus V at R sub A. Let's pick for R sub A the point infinity, and let's rename R sub B as R. With RA being infinity, this second term here becomes 0, And so VR minus V at infinity is Q over 4 pi epsilon sub 0 R. Recall our mental representation what the potential difference is. It's this integral. 1 coulomb times E is a force. We have a force times a distance, that's work. So VR minus V infinity is the amount of work to move 1 coulomb of charge from infinity to R. It's important to hold on to this mental model. We'll see what it means is that you can only measure potential differences between points. You can't measure a potential at a point. This is quickly lost because often, such as in your textbook, V at infinity is defined as being 0, and so you lose sight of the fact that what this term here represents is the potential difference between your point R and infinity. Selecting V at infinity equals 0, as your textbook does, means the potential at location R is Q over 4 pi epsilon sub 0 R. But this still represents the work to move 1 coulomb of charge from infinity to R. It would be equally valid for me to pick 2 volts as the potential at infinity. In this case, with V at infinity being 2 volts, our potential at location R is Q over 4 pi epsilon sub 0 R plus 2 volts. Here is the plot of V sub R with V at infinity chosen as 0, and here is the plot of V sub R with V at infinity chosen as 2 volts. This uppercase R here should be lowercase r, our radial component and spherical coordinate. What happens by choosing V at infinity as 2 volts instead of 0 is just a shift of the total potential curve as a function of position. If you compute V sub RB minus V sub RA for either curve, this potential minus this potential, or this potential minus this potential, you would get the same result. Electrical potential is like gravitational potential energy. You can only measure the differences between 2 points. Let's assume you're out walking around in a desert. It would make sense for you to define the zero of gravitational potential energy as the floor of the desert. So if you jump up, you would gain potential energy. But say the desert you're walking around to is in Arizona, and you come to the Grand Canyon, and your identical twin is at the bottom of the Grand Canyon. Your twin says, I'm at the bottom, and where I am is the zero of potential energy. So who is correct? Well, they are both correct because you can't find the location of zero potential energy. You can only determine potential energy differences. The Grand Canyon is 1,800 meters deep, and let's assume you weigh 150 pounds or 68 kilograms. Your twin could climb up to the top of the Grand Canyon and measure how much work it took to get to the top, and would find it took 1.2 times 10 to the 5th joules. You could jump off the Grand Canyon and turn your potential energy into kinetic energy, and you would measure your kinetic energy when you hit the bottom as 1.2 times 10 to the 5th joules. So you would each measure the same potential difference, and you are each equally valid in choosing your reference for your measurement of your potential energy, your gravitational potential energy. An equipotential surface is a collection of all points that are at the same potential. So the potential difference between any 2 points on an equipotential surface will be 0. Here I'm showing the electric field intensity for point charge at the origin. And here is the electric potential field with V at infinity set to 0. So for a point charge at the origin, the equipotential surfaces are going to be spheres centered at the origin. Notice that the electric field intensity and the equipotential surface are always at right angles. That makes sense because no work is done if you move on an equipotential surface, and it takes no force to move on an equipotential surface because you're at a right angle to the electric field intensity.